Just going to keep this party rolling. There we go. All right, that's kind of where I want to be. All right, guys, everybody hear me okay?
Yep.
All right, awesome. Everybody see my board okay?
Yep.
All right, great. Okay, we're down to a week, guys. We're down to one more lab experiment. So just to recap what we're going to do, you guys all made your precipitates here yesterday. So they're digesting as we speak. So when we get into lab on Tuesday, we are going to redissolve those precipitates back in acid. And well, we have to actually collect them first and clean them. So we're going to collect them and clean them with filter paper. And once we do that, we're going to redissolve them back into acidic solution, and we're going to titrate them with our permanganate. And that's going to allow us ultimately to get back to the calcium ion concentration that you need. All right, so that said, the last thing that we have to do is check out. So we'll probably have time, I guarantee we'll have time to get the experiment finished and get everybody checked out. And then you're going to be done with the lab part. All right, we'll see how far we get. We may not even have to meet on Wednesday for anything. So we're going to see. I can kind of anticipate that we'll be able to finish up the lecture part on Monday, but don't hold me to that. Just judging on where I am right now and what I still want to cover. So you may actually end up getting Wednesday off. So we'll see. All right, so let's just review what we were trying to do here. So the idea was that we wanted to take a galvanic cell like we've been talking about. We wanted to actually turn it into an analytical measuring device. Okay, so this is just a recap of kind of where we ended in class last time. So we had a cathode reaction here that involved iron 3 picking up an electron at a platinum electrode to make iron 2, and we said the iron is going to be the analyte. So that's ultimately what we might want to determine the concentration of. All right, so essentially we could assign a cathode reaction, and that would be the cathode reaction, and we could assign that to the Unearnest equation, okay? So that's going to give us an E cathode. So that's the potential associated with the cathode half reaction. All right. And as you can see, that depends on the E0 of that couple, which you can go look up. And then you have the iron 3 plus showing up in the log term. Now, that's E cathode. So if you take a look here, what you're going to be measuring is E cell. Okay. E cathode is what we want, but E anode is problematic because normally what would happen is that could vary in potential depending upon, for example, the concentration of whatever the soluble species in the anode reaction is. All right, so the goal here was to take that anode half reaction and make it constant. So how did we do that? Well, the way we did that was to assign it as a reference electrode. So we can give it a reference potential. All right, and the way we do that is to actually take the soluble species and pin it at a constant concentration. So at a constant temperature, for example, then the potential cannot change. Okay, so we're locking it down. And the way we do this is with this half reaction right here. It turns out there's multiple ways to do it, but this is the most common way to do it. We're going to use this half reaction here, where we see silver chloride picking up an electron to form silver metal at a silver electrode in the presence of excess chloride ion. And here's the cell notation for that. Now the trick was this. We're going to saturate the chloride ion concentration. Okay, so if we saturate it, for example, by putting an excess of potassium chloride in there so that we actually have chloride ion in equilibrium with the solid KCl because we're beyond the saturation point, the chloride ion is not going to change its concentration. Okay, it might get used up in the reaction or something like that, but it's always going to remain in equilibrium with the solid KCl, which means that its concentration has to remain constant. Okay, so if I take that half reaction as I've described it to you and write it out, here's the Unearnest equation for it. So I'm going to call this E ref. It's the same as E anode above. Okay, so It's got an E0, which I can look up. Obviously, that's constant, RT over NF. As long as we're at a constant temperature, we're good there. And notice that in the argument of the log term, I've got the chloride ion. If I keep that at a saturated concentration, it remains constant. So that means E reference also remains constant. So how do we do this? So I sort of drew a little diagram of the reference electrode using this couple for you. So this is all self-contained inside of a glass tube, for example. And I've got a silver wire in there. Now all I have to do is put that silver wire in there in the presence of chloride ion, and you'll get a layer of silver chloride solid actually coating out on the wire there. So that's easy to do. My old PhD advisor used to talk about making this kind of electrode, and he referred to it as easier than falling off a log, whatever that means, but he loved Southern witticisms. All right, so I'm going to have the chloride ion in there. I'm going to have solid KCl in there, which is the source of my chloride ion. And then I've got the frit at the bottom. And remember, the frit is basically some sort of a semi-permeable construction there that allows ions to pass in and out. So essentially, the frit's going to act as the salt bridge. Okay, because ions can flow in and out of it. So what this allows me to do is to take this whole electrode assembly and just place it into a solution that contains the iron that I want to analyze. Okay, because the salt bridge is actually coming in as the frit with the reference electrode. All right, so that's actually what's going on. Now, if I go back and I look at my half reaction here, what about the E0? Well, we can go look up the E0 for this couple, and I did, and it turns out to be 0.222 volts. So again, that's a constant. Now, what happens if I actually have the chloride ion saturated as I have it here? So it's not actually changing in its concentration. Well, now I've actually got a measurable reference potential based on that saturated concentration. And that reference potential turns out to be 0.197 volts at 25 degrees C. Okay, so it doesn't vary. As long as the temperature remains constant, that reference voltage is going to remain constant at 0.197 volts, and that's exactly what we need. So when we look, for example, at problems involving the use of this reference electrode, we don't even have to use the Unearnest equation for this half reaction. We can just go right to that value, which is very nice. Okay, so now, if I want to come back and set up a cell equation, my E cell, remember, is always equal to my E cathode minus my E anode, right? And now I know that my E anode is going to be 0.197 volts. Okay, so it's constant, just like we said it needs to be. So now if I want to define E cell, here's how I would do it. In terms of the ion couple that I originally gave you, okay, it's going to be the E naught for the cathode, okay, which again, that's that iron 2 plus 3 plus couple that we can look up, minus RT over NF times the natural log, and this is just going back to what we had before. It was the ratio of the iron 2 plus concentration over the iron 3 plus concentration. So I should put those in brackets because those are molar concentrations. Okay, so I'm going to take that whole thing because that's E cathode, and I'm going to subtract from it 0.197 volts. Okay, so now what does E cell depend upon? Well, E cell depends upon what's happening here in the argument of the log. That's the only thing it's going to depend upon because everything else in here is constant. So ultimately what we're talking about here is any change in the iron concentration that we're going to see. All right, so that's the whole business. Now, let's take this idea and let's apply it to an actual problem and see what we can come up with. So any questions at this point in terms of what we're trying to do here and why it works? All right, good. So let's do this in terms of a potentiometric redox titration. So this is actually something you'd really go into the lab and do. I'll bring this down so I can write better. As a matter of fact, you guys don't do it anymore, but in the old 123 lab that you guys all took last semester, we actually did one of these. And it was actually, I believe, this very same experiment. So in this case, let's say the analyte is going to be chloride ion. So that's what we want to ultimately determine the concentration of. Okay. The titrant, so we're going to titrate this, is going to be silver ion. Okay, and we're going to do that at or in the presence of a silver electrode. All right. So let's take a look at what the experimental setup would actually look like, and then see if we can make sense as to what this would actually end up doing for us. All right, so I'm going to do this as a single beaker here, because remember, I'm going to use the reference electrode, which is kind of a self-contained unit, if you recall. So here's my beaker. Okay, so I'm going to put my reference electrode in there. So I'm going to draw it kind of the same way as I did before. Put my silver chloride reference with the frit there. And then it's got the silver wire that comes down in it like that. All right. Now, the other thing I'm going to put in here is my silver electrode. So I'm just going to bring that in, and I'm just going to make it like a coiled piece of silver here that's sitting down in the solution. So that's going to be my silver electrode. You guys might say, well, where's the salt bridge? Well, remember, the salt bridge is actually the frit of the reference electrode in this case. Put a stir bar down here. That's all that little guy is. That'll be my reference electrode. It's a silver chloride reference electrode. And we just talked about. All right. And now what I need to do is I got to tie these together, right? So I've got everything tied together in the solution, but I also need to tie everything together in terms of the electrode. So I'm going to take a voltmeter here, because I want to actually measure the voltage difference between these two electrodes. So I'm going to tie that one there. I'll tie a lead down here to the silver electrode. So the voltmeter is going to tell me at any given point what the voltage difference between the two electrodes, the anode and the cathode, actually is. And then, of course, I'm going to have a burette up here. So I'm going to have a burette. There it is. We're going to stopcock there so we know what it is. And the burette is going to contain some sort of silver solution. So we'll give it a concentration, because we'll probably end up using it here a little bit later. So the burette's going to contain 0.0183 molar silver nitrate. So if it's silver nitrate, we know that's a soluble salt, so it dissociates 100%, so it actually contains 0.0183 molar silver ion. Okay, so that's what's in the burette. We'll be dropping that down into the solution. And then, of course, the solution has to have chloride ion in it, because that's our analyte. All right, so that's what the experimental setup's going to look like. Now, what I'm going to do here is I'm going to actually try to calculate a cell potential. Okay, so we're going to treat this kind of like a regular titration problem, like we did before. Because remember, I think we did a complexometric titration problem. And you guys in dynamics have done a bunch of acid-base titration problems, right? Where you know the concentration of the acid and you know the concentration of the base, and you have various volumes that you add to each other. And then you can calculate the pH as you go. Everybody's done those problems, right?
Yep.
With ice tables and if tables and all that business. Okay. So this is going to be the same kind of thing, only now it's going to be a redox titration. So rather than using our pH equation like we would, we're going to use the Unearnest equation to calculate the cell potential at any given point in the titration. Okay, so that's what we're trying to do. All right, so we got an anode reaction. Let's go ahead and define our anode and cathode reactions first. So the anode reaction is going to be the reference electrode. So here it is. It's the AgCl, and we'll write it as a reduction, because that's what we do, right? Always write these as reductions. And you get your chloride ion. All right. There's your anode reaction. How about the cathode reaction? Now the cathode reaction is going to involve the silver ion, okay? Because remember, I'm titrating with silver nitrate. So I'm putting silver ion in there. So I've got Ag1 plus aqueous picking up an electron. And that's going to take me to silver metal. Okay. Now you're probably looking at this and going, but wait a minute. In the cathode reaction, I don't really see any dependence on the chloride ion. Okay, so you're probably wondering, how do I actually bring this back to a dependence on the chloride ion? Well, you're going to see. Okay. So let's go ahead and write the Unearnest equation for this. So we've got E cell is always equal to E cathode minus E anode. Okay. So let's go ahead and write this out in terms of both things. E cell is going to be the cathode. So we'll go ahead and put that in brackets. So that's going to be the Unearnest equation for the cathode reaction, which everybody ought to be able to write at this point, right? So it's the E0 for the silver Ag plus silver solid couple. Okay, so that's we go look it up. All right, plus RT over, or sorry, minus RT over NF times the natural log of, take a look, products over reactants. So that would be 1 over the concentration of the free silver ion, right? Okay, so there's E cathode. Everybody good with that? Then we're going to subtract from that E anode. Oh, but remember, we know the potential of the anode reaction because we're keeping the chloride at a saturated concentration. Okay, so that's going to be minus 0.197 volts. So I don't have to do anything with that except just subtract it from E cathode because that's constant potential. It's positive 0.197 volts. Okay, so really, what's the only thing? And by the way, that E0 we can go look up in the table. It's 0.799 volts. So what's really the only thing changing in here? This whole equation, what's the only thing changing that E cell is going to depend on?
The silver ion concentration, which is our
Yeah.
titrant.
Yeah, this is it. That's what E cell is going to depend on. And that's going to vary because, again, we're titrating with that, right? So we're going to be adding silver ion with the burette. So we're changing the silver ion concentration in the solution as we titrate. But here's the deal. What does the silver ion concentration depend on? In other words, let's go back to the cell up here. I'm adding silver ion to the cell, okay? And the potential of the cell depends upon the concentration of the silver ion in the solution. But do you see anything in there the silver ion might react with?
Cl minus.
Yeah, chloride. What happens when silver ion and chloride ion find each other?
They precipitate.
Yeah, you make it precipitate. You make AgL solid. Bingo. Okay, so now we've got something that links the silver ion concentration back to the analyte, don't we? So Ag1 plus depends upon the chloride ion concentration in the solution via the KSP reaction. Okay, so remember what the KSP reaction is. Well, remember the reaction, it's this, AgCl solid coming apart to form the ion. So you make silver ion, and you make chloride ion. Okay, and that reaction is governed by, among other things, the KSP. So we can write the KSP relationship for that. KSP is going to equal to the concentration of the products over the reactants, right? So that's going to be your Ag1 plus times the concentration of the chloride ion. You guys done KSPs and dynamics yet?
Yep.
Yep, I figured as much. Yeah, you probably should have gotten there. KSPs and KFs and all that stuff should have gotten there by now. Okay, so you've seen it twice. All right, so that's the KSP for that reaction. Now I can go look that KSP up, right? So it turns out that, looking to see if I have it anywhere, I should have it someplace here. I think it's 1.8 times 10 to the minus 10th. So it's really tiny, right? So here's the question. As I start to titrate the silver ion in there, what's going to happen? It's going to react with chloride ion. So am I going to have any appreciable amount of silver ion in there when I first start titrating it in?
No.
No, because it's going to couple with chloride and it's going to go to the solid, right? Now, that's not to say I won't have any, because what's going to happen? That silver chloride is going to actually redissociate to give a little bit of silver ion back, but it's giving it back in the presence of the common ion, which is the chloride ion. So until I get to the equivalence point, I'm really not going to have a whole lot of silver ion in there. But then once I pass the equivalence point, now the silver ion goes into excess, doesn't it? So there's no more chloride in there for it to react with. So now it turns out the free silver ion kind of takes over in terms of defining the E cell, because there's no more chloride in there for it to react with. So you can imagine I'm going to actually end up getting something that looks like a full-blown titration curve out of this thing, sort of depending upon where we are in the titration. Okay, so you always have to think about what's my source of silver ion once I put it in the solution. Okay, is it coming from the dissociation of the insoluble salt? Or have I gotten past the equivalence point and now it's pretty much just being dumped in there and it's not reacting with anything? Okay, so that's sort of where we have to think about this. Just like any other titration problem we do, we have to think about what's in the solution, right? What relative amounts of stuff do I have in the solution? All right, so let's take a look at the actual example. Okay, so let's write it out here. I've got 25.00 milliliters of solution containing 0.0256 molar chloride, I'm titrating with 0.0183 molar silver ion. We'll just put it Ag plus. We know we're actually putting it in there as a silver nitrate solution, but we know that it's going in as silver ion. All right, so that's the setup. Now, what we'd like to know, and this is what we do in any titration problem, if the information is not given to you up front, is we need to know where the equivalence volume is, right? So I need to know what the equivalence volume of the silver ion is, so I know where I am in the titration. Am I before the equivalence point? Am I at the equivalence point? Or am I past the equivalence point? Okay, so we always have that reference point we have to find. So part A is going to be that. What's the equivalence volume? All right, so we know how to do that, right? That's just basically a mole-to-mole relationship based on our KSP reaction that I wrote up there. So we're going to start out with our volume of the chloride, because why do we start there? Well, because we know the concentration of the chloride and we know the volume of it. If I have volume and concentration, I can get to moles, can't I? Okay. So here's what we would do. We can say 25.00 milliliters of the chloride ion. And can we use just millimoles and milliliters? I think that works out pretty well, because then once we have that, we're good to go. Let's see, I have 0.0256. And that would be millimoles of chloride per milliliter of the solution, right? So we'll just put milliliters of chloride there. Okay, so what does that give me? That gives me millimoles, doesn't it? So now I need my mole bridge. So what am I trying to relate in that mole bridge? We'll go back up to the KSP reaction that I've got. I'm trying to relate these two things to each other, right? So I've got a 1-to-1 relationship there, so I can do that. So I know that for every 1 millimole of chloride, I'm going to have 1 millimole of silver. Okay, see how we're doing. Mils cancel with mils, millimole chloride. And now, to get an equivalence volume, I also have to use the concentration of the other species, the silver ion. So I know that for every 1 mil of the Ag plus solution, I have a concentration of 0.0183 millimoles. And that's silver, right? Okay. So now millimoles of silver cancel with millimoles of silver. If I did this right, I'll have my milliliters of silver ion, and I get 34.97. All right, so that's my equivalence volume. That's going to be the volume of silver ion I've got to put into the solution to get to the equivalence point. In other words, to react with all of the chloride that's actually in there to begin with. Okay, is that okay with everybody? We've done tons of calculations like that before, so that shouldn't look new to anybody. All right, so let's look at part B. Now we can start the titration. So I want to know, what's E cell? What's the potential after 20 mils of the silver ion have been added? All right, so first things first, guys, where are we in the titration? Am I before the equivalence point, at the equivalence point, or beyond it?
Before.
I'm before it. So I've just added 20 mils of the silver ion, and I know I need 34.97 to get to the equivalence point. So I'm before the equivalence point. Okay, so let's do this. I'm going to go ahead and calculate the molarity because I want to see what happens here in terms of a Q versus K type situation if I could. Okay, so I'm going to go ahead and just calculate that. So let's see, I've got an Ag. So I'm just sort of checking myself here. AgCl solid. Okay, we know we're going into Ag1 plus chloride 1 minus. Okay, so I need the concentrations of both of those ions in there. All right, so what about concentrations? What do I have to do there? Well, before I let anything react with anything, I kind of need to account for dilution, don't I? Okay, so do I have a total volume? What's V total here? And there's multiple ways I could have worked this problem. I could have gone right to moles if I wanted to, but I just want to check my Q versus K first. So what's my V total?
45 milliliters.
45 mils, good. Okay, so if I want to calculate my molarity of my Ag1 plus, here's how I'm going to do it. And you guys can do it just as well. So I'm going to take my 20 mils that I'm putting in there, multiply it by the molarity, 0.0183. And that's going to be millimoles. I'm just going to leave it per milliliter since we're just talking about the Ag here. And now what I have to do is I'm going to divide that by the total volume to get the diluted concentration. So we'll do that as 45.00 mils. Okay, and you guys can check my math here. When I do that, I believe it turns out to be 0.008133 molar silver. Okay, that's the diluted concentration of the stuff. What about the chloride ion? Well, we can do the same thing for that. Okay, so I'm going to take the volume of the chloride ion solution. That's the 25 mils, right? So that's going to be 25.00 mils of it. Multiply it by its concentration, 0.0256 millimoles per mil. Okay, now again, I'm going to divide by the diluted concentration. So that's going to be 45.00 mils. Okay, and when I do that, I end up with 0.01422 molar chloride. All right, and if we're going to be picky about sig figs, we can do that as well. All right, so let's calculate a Q. That's an ion product, right? So it's basically the concentrations of each thing that I've got. So I need the concentration diluted of the silver ion times the concentration of the chloride ion. I got both of those. So it's going to be the product of those two. All right, and my ion product turns out to be 1.16 times 10 to the minus fourth. Now, I want to compare that to my KSP. Now, we went and wrote a KSP up there, didn't we? That's the number we can go look up. Oh, there it is. It's 1.8 times 10 to the minus 10th. My ion product is 1.16 times 10 to the minus fourth. So we can see here that in this situation, that Q is greater than my KSP. Now, what do we say when Q is greater than KSP? Do we have a precipitate or no?
Yep, we have a precipitate.
Precipitate forms. In other words, we're beyond saturation. All right. So now, let's kind of turn this around because we want to actually show the formation of the precipitate now that we know that we have it. So I can do that by showing Ag1 plus the chloride 1 minus. Now, am I going to use an ICF table here or an ICE table if I want to describe this as I'm writing it?
Ice with a KF, right? Or your inverse of your KSP.
It's the inverse of the KSP. What's that going to be, a big number or a small number?
Big number.
Big, really huge, right? So if I have a really huge number, I use ICF, right? So in other words, I flipped the KSP reaction here. So now I have a large K for this. That K is equal to 1 over the KSP, right? Which is a really big number. So we're going to assume this goes 100% to the right, at least at our first crack here. So I can do an ICF. Now remember with ICF tables, I can use either concentrations or moles, doesn't matter which. I've already got concentrations, so I'm just going to stick those in because that's what I calculated, right? So let's see here. For the silver, I've got 0.008133, keeping all the numbers. Chloride, I got 0.01422. Silver chloride, we don't worry about. Wouldn't show up in the law of mass action anyway. Now look at this thing. Which one's your limiting reactant, guys?
It'll be your silver.
Be your silver. So that's going to dictate how much of each component we're going to lose. So 0.008133. So all we're really doing here, guys, is a limiting reactant calculation, right? So I'm not going to have any silver ion left over because it was our limiting reactant. Chloride ion, its new concentration is the difference here, which is 0.0061 molar. Okay. So now, here's the question. I want to know how much silver ion I've actually got in the solution. So I've run this reaction 100% to the right to make the precipitate. How am I going to get back to the silver ion concentration that I've actually got in the solution? What do I have to do?
Reassociate.
So now I got to reverse the reaction, right? So I've let the reaction go 100% to precipitate as defined by the limiting reactant. Now I got to flip the reaction and let it redissociate to make some silver ion. Oh, but look, it's being made in the presence of a little bit of chloride ion. Common ion effect problem, right? So now I can actually treat it as an equilibrium as governed by the KSP. Way back, we worked problems like this, believe it or not. So now I'm going to use an ice table because now this is governed by a really tiny equilibrium constant, the KSP. Silver chloride, we don't worry about. Okay, so now let's take our F line and plug that into the I line here. So it looks like I've got no silver ion to begin with, and I've got 0.0061 molar of chloride ion. So now I'm letting the reaction redissociate to make some silver ion in the presence of the chloride ion, common ion effect. Which way does this reaction have to go?
To the right.
Got to go to the right. That's the only option I've got. I got to make some silver ion. Okay, so it looks like I'm going to have X here, we'll add down, we get X, we get 0.0061 plus X. Everybody okay with that? Okay, so now I can plug all this back into the KSP. Remind ourselves what the KSP is. It's the equilibrium concentration of the silver ion times the concentration at equilibrium of the chloride ion. And we have both of those. And that's all equal to the KSP, which is 1.8 times 10 to the minus 10. Again, that's the number we go look out of the table. All right, so now I'm going to bring everything from the E line down. So let's see, silver ion becomes X. Never done this calculation before, have you? 61 plus X is equal to 1.8 times 10 to the minus 10th. Okay, can we make the math easy, guys?
Yep.
Yep. Can I get rid of an X?
Yep.
Which one?
The additive X.
We'll get rid of the additive X. There we go. So what I've really got is 0.0061X is equal to 1.8 times 10 to the minus 10th. Should be an 8 there. There we go. Solving for X is easy at this point. So now the X is going to equal to, I get 2.95 times 10 to the minus 8th. And that's the molarity of the silver ion. And probably ought to be good to 2 sig figs there based on the KSP value. Okay, so am I done? No, I'm not done, because now I've got the silver ion concentration, but I'm trying to get E cell. So what do I have to do with that silver ion concentration now that I've got it? Well, yeah, I got to go plug it back into the Unearnest equation that we actually had, right? So remember what that looked like? So we could say that E cell, we wrote it up above. Let's go ahead and plug everything in, right? So this is for the cathode side. So this is the silver couple, 0.799 volts. Okay, that's at E0 we noted above for that. Minus, let's do 8.314. That's 298 Kelvin, right? We're going to assume it's at room temperature because we haven't been told otherwise. How many electrons are getting transferred in this half reaction?
1.
1, good. Times the Faraday, 96,485. Well, we showed last time this comes out to units of volts because it's a joule per coulomb times the natural log of, guess what? Products over reactants, right? So it's going to be 1 over the silver ion concentration as we wrote it in the half reaction. So that's going to be 2.95 times 10 to the minus 8th down there. And then what we're going to do, we're going to subtract from that the reference potential, minus 0.197. So that's that constant voltage we get from the reference electrode. Okay, so now we can get E cell. So if you work all this out, just so you guys can check your math here. If you do all of this, you end up getting 0.445 volts. Okay, so then when you get your E cell, your E cell turns out to be 0.157 volts. Okay, so that's our voltage that we would actually measure on the voltmeter for this specific addition of the silver ion. And again, it's important to recognize that it depends only on one variable, and that's the concentration of the silver ion. And what dictates the concentration of the silver ion? It's the KSP situation or condition. Okay, and that's true in this case because we formed a precipitate. All right, everybody good with what we did there? I kind of like this because it's kind of pulling back a whole bunch of stuff that we did early in the semester and tying it into some new stuff that we're doing here with the redox side. So this is really good from a review perspective, but it's also good to show how we can use that information to do something a little new and different. That's probably the hardest one we got to do. So I think we can get through part C. We're just grinding along here, guys. So next thing obviously is what's the potential at the equivalence point? So anything before the equivalence point, we'd work the same way as we just worked that prior problem. But now when we get to the equivalence point, I want to know what the E cell there is. All right, so let's go back and get our moles of chloride. Now, once I get the moles of the one thing, I know the moles of the other thing because they have to be the same at the equivalence point, right? So let's go ahead and start from the point of view of the moles of the chloride because I know how much of it's in there. All right, so I've got it in terms, and I'm going to go ahead and get it as moles instead of millimoles here because I'm doing it in terms of moles. So I'm going to go ahead and use my volumes in liters. I'm going to go ahead and just use molarity straight up. And you end up getting 0.0000366 moles of chloride. Now, if I'm at the equivalence point, then I know that the moles of the silver have to be the same. All right. Now, in this case, I don't need to verify here that I've got the precipitate. We've kind of already done that in part B. Okay, so if I'm adding even more silver ion, I know I'm going to make more precipitate. Okay, so I don't really need to go back through that verification, which is kind of why I went to moles instead of using molarities. So let's do the same thing as we did before, just to verify kind of where we are. Let's make the precipitate first. Okay, we know that's going to go all the way to the right. Okay, and we can use an ICF table here. And remember with ICFs, doesn't matter whether I use moles or if I use molarities. I got moles, so I'm going to use moles. They're the same. Who's the limiting reactant?
Both.
Both are. Yep. That's the definition of the equivalence point. So I've got a big old goose egg there, big old goose egg there. Now, how am I going to determine how much silver ion I've got in the solution now? What am I going to do?
Redissociate.
Yeah, redissociate. So flip the reaction and let KSP do its thing. Now I'm going to use the double arrow because we're dealing with equilibrium again. And we're going to proceed just like we did before. But now we're going to use an ice table. Okay, so I don't have any, I don't need to worry about that. Now, initially, I don't have any silver ion, I don't have any chloride ion. So this reaction's got to go to the right to make some, right? Now, how much? I don't know. It's going to be governed by the KSP. So I'm going to let that guy be an X, let that guy be an X. But now notice that we're not dissociating in the presence of any common ion here. This is just a straight up KSP problem. As if I just took solid AgCl, dumped it into a beaker and said, okay, what does it dissociate to? All right, so now it's kind of an easy problem to solve. Plugging back into the law of mass action, I just get x squared is equal to the KSP, which is what, the 1.8 times 10 to the minus 10th. Okay, take square root of both sides, just a straight up KSP problem. And you get 1.3 times 10 to the minus 5th. Okay, so this is the only place that happens, is right at the equivalence point. Because otherwise, you're going to have an excess of one ion or the other in there. The only place you do this calculation is at the equivalence point. Okay, so let's go back to our E cell now. Do the very same thing we did in part B. All right, my E0 was 0.799 for the cathode. Minus RT over NF. Again, the only thing that's going to change here is going to be the silver ion concentration. Times the natural log of 1 over the silver ion concentration. Okay, why? Well, because that's the way we wrote the half reaction, right? So that's going to be 1.3 times 10 to the minus 5th molar. All right, and then I got to remember subtract from all of that the 0.197 from the reference electrode. Okay, so if you work all this out, you guys can verify your numbers here. This will end up being 0.288 volts. Sometimes it helps just to see where you are. Then you do the 0.799 minus the 0.288. Then you subtract from that the 0.197, and your E cell is going to be equal to 0.314 volts. All right, so did the voltage change from part B? What did we get in part B? We got 0.157, and in part C, we got 0.314. So notice the voltage is increasing. Why is that? Well, because the silver ion concentration is actually increasing a little bit. Okay, so the voltage is going with it. All right, any questions about that so far, guys? Now, I think I'm not going to get into part D. Part D obviously is going to be what's the cell potential after the equivalence point. So let's just go ahead and define it. And then on Monday, we'll come back and we'll do it. So the question is, what is E cell after 40 mils? So we're beyond the equivalence point at this point. I'll show you another interesting thing that I failed to mention about part C. Did we ever have to calculate a diluted concentration there?
No, because the moles all canceled out.
Yeah, because the moles all canceled out. That's basically exactly right. Okay. So then in the end, we were in good shape. So, you know, it's just a straight up dissociation when the moles of the reactants basically cancel out. And then when we just solve the good old KSP reaction, we get a molarity automatically back out of that. But that's the only place where you don't actually have to calculate molarities. Okay, so even in part D, we're going to have to come back and we're going to have to account for dilutions. All right, any questions? Guys, we are seriously wrapping this up. I think we'll have no trouble whatsoever getting this wrapped up on Monday and getting where we need to be. So plan on Monday being pretty much the last class, then Tuesday being the last lab, and then I'm cutting you loose until final exam time. So we'll take some time on Monday to talk about the final as well. All right, everybody good?
Yep.
All right.
All right.
I'll see
Have
you
a good
guys
one.
on Monday.